don't know when are we starting exactly? At what time?
Right. We have uh, we have waited a while for others to join, so we are going to start immediately. I want to extend warm greeting to each and every one of us who made it to join us in this beginners course on computational chemistry. This is a class that defines your knowledge, your foundation. Yeah, because most times when we run classes on computational chemistry, we often encounter students who just try to understand what we are saying because of they lack uh, because they lack the basic knowledge because they lack the basic knowledge of what the concept is all about. And that was the reason why we have to initiate this class on computational chemistry. So once again, I say thank you. I'm going to quickly share my screen right away. So we proceed at the same time. Yeah, it will be an interesting session tonight. Okay. Right. Can you see my screen?
Yes, sir.
All right.
Yes, we can
Uh,
see.
okay. I will talk a little bit. Some person said I like talking too much, but that is by the way I need to talk so you understand what we are saying. This is foundations of computational chemistry. So this is beginners course. Here we have students, undergraduate students, postgraduate students, and lecturers. So it's a mixed class. I'll be careful in the choice of words. Uh, okay, we should ask ourselves this question: what is computational chemistry? So we'll begin from there. Meanwhile, we sent out some textbooks. So in the drive, there are some textbook. We we sent out about five textbook. So I don't know if some of you have seen it. So you can take your time to study those five textbook. They will help you to have a better understanding on what computational chemistry is really all about. So those textbook will help you. It is part of our culture that in all our training we give our students related tests and material that will help them. Okay. So what is computational chemistry? Computational chemistry is a branch of chemistry that is a branch of chemistry that uses computational simulation and mathematical algorithm. So it's a branch of chemistry that uses mathematical simulation, computer simulation, and mathematical models to solve chemical problems. So it is that aspect of chemistry where we learn how to use computer algorithms that we are built with mathematical models. How we can use them to solve problems, to solve chemical problems. So computer scientists with the knowledge of chemistry, we are able to build some softwares that these softwares have been programmed to solve chemical issues, chemical problems, to draw chemical structures, to manipulate chemical reactions, to predict chemical synthesis. So all what these softwares can do is basically based on computer simulation, computer algorithms. So the software can do a lot. anything you want to do in chemistry, there are softwares that can do it for you. It's just for you to be able to know the exact softwares that can do this. So that idea of using computer to solve chemical problems is called computational chemistry. It is not yet a course on its own in Nigeria, but currently in the CCMAS, some schools have incorporated computational chemistry as part of their undergraduate courses. Some schools are currently offering it at year 2, year 3, some at 400 level. Even those in Polytechnic, they are doing it, mostly the chemistry departments in the Polytechnics, they are doing it as part of their courses, in final year. So soon, we are seeing that it will not be a discipline on its own. It's still new to us in this part of the country, and every day by day, different software keep emerging due to challenges we have encountered in chemistry, challenges in research. So once you have a challenge, something you need to do, you can now build a software that can do it. So we are looking forward to see chemists who can venture into software development. So they begin to develop softwares that are used in chemistry discipline. So that's how we have gathered here. We are going to look at some of those softwares and see what we can do. And we are beginning with the basic, that is ChemDraw. Because once you are a chemist, once you have business to do with chemistry, then you must know your ChemDraw very well, and that is why we are here. So it predicts molecular properties. So this computational chemistry tools helps to predict molecular properties, reaction mechanism, and material behavior. So we can use softwares to know the properties of a molecule, the reaction mechanism, like Scientia. Scientia is used to predict reaction pathways. All these are based on models that has been created in that software, programming language that we are used to build that software. You can use it to know the behavior of materials at different conditions, even without conducting any physical experiment. So I will try to be fast. Now, by solving equations derived from now, the basic behind this course is based on chemical equations derived from physics and chemistry. Most of these softwares we use, they were built by Schrödinger equations. They are built by Schrödinger equations, mainly quantum mechanics and classical mechanics. So I don't want to go into this part. I just want to see that we rush and enter what we have. Then computational chemistry serves as a bridge between experimental chemistry and theoretical chemistry. So we are saying that before you go to lab, we are bringing a new workflow that before you go to lab, conduct your experiments using in silico, that is computational. So it is a bridge now between what you read in textbook and wet lab. So from reading literatures, before going to your wet lab, you must pass through computational chemistry. So it will help you to justify your literature basis, help you identify better outcomes before you can proceed to your wet lab for validation. So it enables chemists to simulate scenarios that are difficult, expensive, or impossible to test in the laboratory. So there are some experiments that are too expensive, too difficult, impossible to do in the lab. We can now perform them through the use of computational chemistry. There's a course we are trying to put on together for chemistry, that is virtual chem lab. Some of us must have heard about that, virtual chem lab. And when we are done with that course, we are encouraging schools that do, one reason why we don't conduct practical in our various institutions is because we keep complaining of consumables, no reagent, no reagent, no reagent, no chemicals. So on that note, you can now explore in virtual chem lab where you conduct your experiment virtually. Those experiments you want to do the same way they will be done in the lab. You can example them and conduct them virtually. So that same way you do titration by mixing acid and base, having your burette, you do it, you can have that setup virtually and see it run. In fact, you have a better result because most times you encounter challenge doing color change, doing your endpoint. But in virtual chem lab, it gives you a clear endpoint. So that is one of the importance of this computational chemistry. I would not like to go through the history. I will just skip this part because it started a long time ago, but I will just have to skip it. Now, there are branches of computational chemistry. We have the quantum chemistry. Quantum chemistry uses quantum mechanics to study electronic structure of molecules. Like the ChemDraw we shall be using is usually built by quantum chemistry principle. Quantum chemistry also solves the Schrödinger equation for atoms, molecules, and solids. So those atoms will be using to add atoms, draw molecules. They were possible because of Schrödinger equation. So these are what people did to build those softwares that we shall be exploring in computational chemistry. Another branch of computational chemistry is the molecular mechanics. Yes, the MM. MM is a branch of computational chemistry that treats molecules as classical system. Now, what that means is that they see molecules as a classical object, like as an object that can be set to motion. That is what MM does. Mechanics is all about motion. So that is why doing our energy minimization, the ChemDraw minimizes energy based on molecular mechanics. So it will reduce the energy because it will treat that molecule as an object that can be set to motion. So once it sets that object to motion, it will now calculate the energy available for reaction and the energy as a result of the spatial arrangement of the atoms. So it will help now minimize the energy. So these are the three branches, and it's usually based on force fields. So it uses force fields. There are different force fields. These force fields are used to model structures. Modeling of structure is part of what we are doing in this training. Just like Pyres. Pyres does energy minimization, but it uses UFF. That is why if you observe in Pyres, after you minimize energy, you will see UFFE or EUFF. That means minimize energy. Then you now see a value. That UFF is a force field, and that force field is universal force field, UFF. So in computer chemistry, you can minimize energy using force fields. But in ChemDraw uses MM, which is the molecular mechanics, as a force field in modeling structures. Another area is the MD, the dynamics. We have spoken a lot of. We have really discussed so much on dynamics, where we set an object to motion at different conditions. So you can set an object to motion at different conditions. You can look at the conditions at different time interval, temperature and pressure, and then while that object is set to motion, you look at the stability and the flexibility of that object. That is the whole idea of MD. You check the behavior of a molecule in a system. So all these are part of what we do in computational chemistry. And for you to achieve that, it uses the Newton's laws to simulate molecular motion. Another key branch is chemoinformatics. I want to let us know that you cannot exploit in computational chemistry without the knowledge of chemoinformatics. Just like some of us from biology area, you cannot do well in computational biology without talking about bioinformatics. So as bioinformatics is essential for computational biology, that is also how chemoinformatics is essential for computational chemistry. But we notice that a lot of us doesn't really have that idea or much interest in chemoinformatics. And that is why we have put up this training. So we are encouraging you to quickly join that training. I think we have a training on chemoinformatics. You have seen our advert. That is next week. It's free. That training is free. You join that training on chemoinformatics for life sciences. Here we explore chemical and natural product data. We'll go deep into different database. So chemoinformatics is another major branch in computational chemistry. So one will take our time to discuss chemoinformatics. Come next week, Wednesday and Thursday. So you can register for that training. It's free. Share it to your colleagues. They can enroll in that training. It's free. All right, so that is very important. What it does is that it handles chemical data storage, retrieval, and analysis. So we should have a database where we can store our data, retrieve, and use them for analysis. It involves molecular fingerprints, similarity search, and clustering, where we can group molecules to become one, where we can search for fingerprints, that is molecules with similar identity. We can search molecules with similar structure, that is the similarity search. So we can all do this with chemoinformatics. And our idea is to build our own database. Let me just tell you that so you have it in mind. Your project in this training is to build 5,000 molecules. Without it, no certificate for you. So I'm just trying to tell you now, so you have it, you just bear it in mind. You know to build 5,000 molecules for yourself. You build 5,000 molecules. You are going to identify, give them your own ID. You give them your own ID, like hand 1, hand 2, hand 3, hand 4, hand 5,000. So just give them your own ID. That is what we will do in this training. That is the whole end, the summary of our work. Now, the theories, we have talked about these theories, which is the Schrödinger equations and others, the Oppenheimer principle. So these are the foundations, the Hartree-Fock method. These are the theories that are used in building these softwares. I'm looking forward to a time where we'll start to develop our own software by ourselves, our own computational chemistry software. So we'll start to develop by ourselves. We have density functional theory, which focuses on electron density. So these are the foundational theories. Then the advantage of computational chemistry is that it helps to reduce cost of experiment that ought to be expensive in the lab. Once you have good knowledge of computational chemistry, you can reduce those costs. Like take for instance, you want to identify a lead compound for moringa leaf, and you are able to identify 1,000 compound, and now you want to know the lead. You want to identify the lead compound for a disease. Yeah, for a disease. Now that means that if you're not using a computational chemistry, you're going to spend money in isolating each of those 1,000 compound, or you extract, you synthesize each of those 1,000 compound and begin to do high throughput screening HTS on each of them on your target, so you can identify your lead. But with the knowledge of docking, with the knowledge of docking, you can do virtual screening. You can do virtual screening, which will enable you to identify your lead. So it saves time, it reduces cost, it predicts the properties of molecules before synthesis. So I can know the properties of a molecule, the behavior of this my molecule, even before I synthesize it. Even like I said about Scientia can help you to develop your synthetic routes. So you can know if this synthesis is feasible or not without going to the lab. I could remember I did a synthesis of which compound 2 years ago. I was able to synthesize purpurine. Purpurine, that is 910 hydroxy anthracene. So it was easier for me because I've already developed my pathways using computational chemistry. So it's as if I have already conducted the synthesis using computational chemistry tools before coming to the lab. So I'm not going there to waste reagent or waste time. I've already developed the conditions, the predictions. I've developed the time, my percentage yield. Yes, I've developed my percentage yield, my actual yield, and other things. So I've known the various conditions that I must subject each pathway to before going to the lab. So it becomes easier for those in synthesis. You can know the properties. Now it exploits reaction mechanisms and atomic levels. So I've talked about that. It helps to accelerate drug and material discovery. So with the knowledge of computational chemistry, you can now speed up the rate of drug discovery. It becomes faster. And even in material discovery, in material science, you can now develop materials used in the industry. You can develop materials used in industry and their applications. So you can do that so fast with computational chemistry. In fact, this is dry lab. So this is dry lab. And I like I told my student today, I told them today that we are moving from wet lab to dry lab, and every one of us at final year should be exposed to dry lab techniques. Should be exposed to dry lab techniques. So that is where we are now. One of the advantages is that it simulates dangerous or impossible experiments easily or safely. So there's some experiments that are toxic, some that are impossible to be conducted in the lab. We can now easily do them with computational tools. Right? Are we together? Hello.
Yes.
Oh, thank you. I just want to have that affirmation.
We are together.
Yeah. Despite what we can do with computational chemistry, we still have limitations. One of the limitations is a high computational cost for large systems. Like when we are discussing during our webinar on the 17th, on the 17th of this month, last 2 weeks, the challenge we have in some of these computational softwares is we need a super systems to do that. If not, your system will crash. I shared an ugly testimony that my system have crashed up to 4 times. I remember late last year, the last one, I saw a software and I love the software. I want to learn it. So immediately I installed the software. You know, when system is running, showing that circular sign that something is running, my system was just like that for like 2-3 hours. Before I know, system closed, crashed. So these are the challenges we are having because there are some of the software that your system cannot carry. And that is why you be careful in some of these softwares you are downloading. I've had ugly experience. We have just you know these white men. You just attend the conference, a webinar. They'll be telling you some software they are using and how good it is. You to Mumu go download them. You search for them online as you download. You don't know that your system cannot carry it. Is there any system we buy 500,000, 400,000, 200,000 here in Nigeria? You want to run one so my dear, there's a challenge. You need high professional cost for large system. So we are just doing the ones that our system can be able to perform. That is a big limitation to us. Then in this course, your accuracy depends on the method you are using and the basis you are setting for your work. So here, accuracy depends on the user because you are the one managing the software. So if you want to have a precise result, then depend on the user. So you know what you want to do. You know how the result want to be. So most times we don't control the result, and it's now a challenge. We don't control the result. Our job is just to input, go out to input, and we'll get the outcome. It's a challenge too. There's a need for expertise to interpret results correctly. And I've seen people who love talking by hearing it, but they could not even interpret or defend themselves. But they love to do your work on talking. So there's a need for expertise in computational chemistry. There's a need for us to have deep knowledge. And most importantly, it cannot fully replace experimental chemistry. I keep saying that even if your mic is on, I'm having a sound, but I'm having a background sound at the background. Right. Thank you. So it cannot fully replace experimental chemistry. So I keep saying it that even if computational chemistry is bridging the gap between CO2 chemistry and experimental chemistry, you cannot delodge, you cannot quickly kick off lab work. The lab work will be there, but the lab work now is reserved for only validation. So all those experiments you want to do in the lab, don't bother yourself. Come to computer and do them. So as I'm talking to you now, your computer is your lab. I keep telling my student that my laptop is my lab. I don't need to build one big thing. My laptop is my lab, and anywhere I'm going with my lab. So in Hendeb, we have a lab that is Hendeb Biophychem Laboratory. Our laptops is our lab, except those who wants to do in vitro and in vivo work. But most of our work is in silico, and this laptop is our lab. So, but we will not say that we can replace experimental chemistry. So we are leaving that for validation. But you see, at undergraduate level, when you give a student a research work to do on computational chemistry, they keep telling us that this is above their level. Is above their level. At final year, is above their level. Then at what is now their level? Their level is like those in biology, in microbiology. Every year you keep doing isolation and identification, antibacterial this, antimicrobial this, antifungal this. So there's a need for we to start in bringing in computational to our undergraduate levels. Like those in chemistry, if your research work is not on heavy metal, if it's not on absorption, if it's not on proximate phytochemical, then I wonder what people are doing. If it is not on PAS, on environmental pollutant, so on water, coagulation and purification, you see that the work is now we have eventually, we are just repeating what we do every year. So there is no new idea. There's no new idea coming forth. We keep repeating. So if we can bring in computational as part of our research, then do wet lab for validation, who can do a better work. We can do a better work. And one of the challenge we have too is approximation method, because these results are predictions. So most times it can lead to errors if not well managed. We have the future of computational chemistry. Our future is AI and machine learning. So towards the end of this year, we are bringing a training on AI and machine learning. That is the future. So we should embrace it. Quantum computing. This is our future. Solving currently intractable quantum chemistry problems. That is where we are going to. Big data and cloud computing. I promise to come up with a training on cloud computing that will help to manage the issue of MD. So I promise that we are putting up training on cloud computing. Here we can do high throughput virtual screening. Instead of you doing just only virtual screening, you can screen millions of compounds at the same time in cloud. Not the one you are doing with Pirates and then you are loading 50 small. So that the system will not overload. This one you can now do high throughput virtual screening, HTVS. So cloud-based collaborative research platforms. So we try to partner with some platform that can enable us to do those work. That is the future. Green chemistry applications. Green chemistry is also where we are heading to. And in Hendeb, I think we are not too many that has put up a training on green chemistry using in silico tools. So that training we have put a lot, and that is coming forth by February from 10th. Immediately we finish the chemoinformatics training, we'll now move into a 1-month training on green chemistry. So I will appreciate if you receive your salary this month and you just try to kill into that training. It is novel. That is the future. Green chemistry application. You can predict eco-friendly reaction conditions. You can model waste reduction process. There are a lot of waste around us. Let's learn how we can convert this waste to useful raw material using in silico tools. That is the idea. It's coming forth next it's coming forth next 2 weeks from 10th of February, just for 20,000. There's a work I designed for this TED Fund NRF grants. And that work, they just approved our concept note. We are now preparing our full proposal. What is the work? We are converting our cassava meal wastewater into bioplastic that can be renewable. We are converting cassava meal wastewater into bioplastic that can be renewable and degradable, the one that you can degrade. So that work, I'm not the PI, but I was the one that conceptualized that work, and we are part of the lead researchers there. We are using in silico tools to do that. Then with our experimental validation, that is what we need in green chemistry. So join us February. The registration will close on 30th, but we'll still extend it. So just for 20,000. That is where we are going to. So computational chemistry is indispensable in modern scientific research. It enables the understanding and prediction of molecular behavior with increasing precision. So once again, you have made the right choice to join this foundational class on computational chemistry. It complements laboratory experiments, drives innovation in drug development, material science, and environmental chemistry, and continues to evolve with advancement in computing technology. There is a work we are planning to do, though the man is now late. The immediate past president of NSF, the US Society of Microbiology, Professor V.O. Wong. We are designing a work on biocoagulants of wastewater. That was in silico, using computational tools. So about suddenly death just took him off last year, and that what just died like that. So you can apply it in your in the environment. It has vast application, and I will just lead you through in 10 minutes. I will lead you through the various applications of computational chemistry. So as you are learning, you open your mind wide to see other areas, research areas where you can apply computational chemistry. So I'll quickly lead us through that now. But while I'm moving to that aspect, do you have a question? Can I take few questions? Before we look at research applications of computational chemistry. So I just want you to be properly guided in what we are doing now. Before then, how many of us have not installed our ChemDraw? Because we shall be using it tonight. Hello?
Yeah, my laptop says I have to install something so I can install it.
You have to
But I
install
have to,
something so you can install it.
yeah, something 2.0, something
NetFrame.
like that.
Is it NetFrame 2.0 or something?
Yes, 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 yes.
You okay? You would have let me know. Okay, I'm dropping
I
right now.
also have the same challenge. I also have the same challenge.
Okay, right now I'm dropping that solution now in the platform. But we ask that those having challenge should let us know. It will.
I sorry, I didn't see it.
The same thing
It's
with
in the
me here too.
it's in the platform. Oh my god.
Laptop just
Hello,
default.
hello, sir.
I'm so
Yes.
sorry.
In my own case, I've installed it to finish level, but I don't get the shortcut or anything what have you for me to open it.
It's the same problem.
Okay. But Jesus sake. But
I've activated it. I've installed it to the last stage, but having
yes.
completed it, no shortcut, nothing for me to be able to open it.
Okay, that one is not a challenge now. If there is no shortcut, you can go to your search. You can see my screen now. You can
Okay.
go to your search and
Okay.
search for ChemDraw.
Okay,
Just type ChemDraw
okay,
and you will see the ChemDraw open, showing you the app.
okay,
ChemDraw app. I have
Okay,
two
sir.
ChemDraws, sir. This one is ChemDraw Professional 16.0. But when people are using this ChemDraw Ultra 12.0. So you see ChemDraw Ultra 12.0. That is what I'm using with you. But me, I used to use the professional ChemDraw, which is 16.0. So, but for this beginner course, I gave you ChemDraw Ultra 12.0. So you just see it. Once you click on it, it will open. That is for the person that has issue with a shortcut to open it. Now, for those of you that have issue with installing NetFrame 2.0, I just sent in the group chat now. I sent a workflow how you can overcome that. So it is right there in the group chat. If you just follow the steps there, and once you are able to activate the NetFrame 2.0, then go back to install the ChemDraw, and then do well to watch the video. Do well to play the video we sent. There's a video in the drive on how to install ChemDraw, so it will also guide you properly. All right. Hope that is okay.
So please, where is the video? Is it the email? Where was the video sent to?
Okay. Professor Excellence, we have not sent yours.
Yes, sir.
Yes,
Okay.
because we
I just
got
really
your
checked.
yes. So what I did
Okay.
was, whenever you join the class, I just have to send you the link first to join this class.
Okay, thank you.
Yeah, because we saw your registration few hours.
lately. Yeah.
So
Thank you.
yeah, you're welcome. So immediately after the class, I shall send you the drive.
It's okay.
All right. Ah, oh my God. And I want us to do hands-on. Okay. Well, we'll do something. We'll still do something. Thank God you have access to the video. So the video will help you to practice the little we shall do today. Now, I want to give you the research applications of computational chemistry. Please, if your mic is on, mute your mic so I can hear myself clear. So I want to give you the research applications. Is that Professor Adeola mic that is on?
Oh, I'm sorry.
Yes, it's the one.
Okay. So I want to give you the research applications of computational chemistry so that you know the areas you can apply this thing. You can see the possible areas where you can apply what you are doing tonight. You will be doing today, tomorrow, and Saturday. So can you see my screen?
Yes, sir. Yes, sir.
So,
Yes,
so
sir.
this is research, because oftentimes when I teach students, what they ask is, where can we apply this knowledge? Is very, very important. After learning computational chemistry as beginner, where can you apply this knowledge of computational chemistry? So a quick one, I have about 25 research applications or thereabout. So I will just show you. Number one is in environmental chemistry. You can do very well in that area. Yeah, you can do very well in that area. You can use it for pollutant protein binding studies, biodegradation pathway prediction, endocrine disruptor analysis, heavy metal chelation modeling, microbial radiation interaction studies. These are what you can do in environmental chemistry. In food chemistry, you can use it for food additive safety assessment, nutraceutical enzyme interactions. I did a work. I presented that work at UNESCO, UNN, where we use OPA. No, not OPA. This okra, the one they call actinocon, the okra. So we use it to formulate nutraceutical. Where it was for diabetes because it has low glycemic index. So people who have diabetes would now tested that okra. So they were eating the okra and it reduced the diabetes. So why the okra is still nutritious, is still medicinal. So you can do a work on that on food chemistry. You can do a work on microtoxin receptor binding, flavor compound olfactory receptor docking. So your flavors or your spices, you can check their effects. Enzyme inhibition by food contaminant. These are possible areas you can work on when it comes to computational chemistry. In analytical chemistry, you can do biosensor target binding simulations, chromatographic interaction modeling, ligand-based assay development, surface binding prediction for sensors. These are some of the work we have done. Some part of it are what we have done in Hendeb. Docking-based spectroscopic probe design. In agricultural chemistry, we can do a work on pesticide target binding, herbicide receptor modeling, soil microbial enzyme interactions, insecticide resistance mechanism modeling, plant growth regulator. You can do a work on that in agrochemistry. In biochemistry, you can do enzyme substrate docking. You can do protein ligand interactions, which is the molecular docking we know. You can do work on metabolic pathway simulation, allosteric site binding studies, cofactor binding modeling. So, giving ideas. If you're in physical chemistry, you can apply it in thermodynamics of binding prediction, free energy calculations of docking complexes, molecular dynamics of dark structures, solvent effect simulation. So there are so many. In organic chemistry, you can do a work on host guest complex modeling. You can do a work on organocatalyst binding site studies. You can do natural product interaction prediction, organic pollutant binding analysis, reaction intermediate docking. Those in inorganic chemistry, you can do work on metal ligand interaction, and that is a coordination chemistry. You can do a work on coordination complex docking. We have a training on nanotech. We are eagerly waiting for that training. Nanotech and metal complexes is coming. I don't know the month, but it's part of our training. So we are using in silico tools in nanotechnology. So you can do a work on metal enzyme active site modeling. You can do work on drugs that contains metal. Environmental metal toxicity studies. You can still do that. People in medicinal chemistry are related. You can do a work on pro-drug activation modeling, enzyme inhibition mechanism studies, ligand target cell studies, off-target interaction prediction. So Zico4, you can do a work on that. People in pharmaceutical chemistry, you can apply computational chemistry in drug formulation, macrophore docking. That is what we did this month. Controlled release mechanism, very important in drug formulation, controlled release. Drug excipient interaction. You can look at how your drug interacts with your excipient. Even drug interaction, you can do some work on those areas using computational chemistry. Drug target binding. So we are giving you the foundation as a beginner. See what you can do with it. So explore. It is like what August Kekule said. Is that it's a deep ocean. The more you go, the deeper it becomes. The more you go, the deeper it becomes. Those in polymer chemistry, you can do that in polymer protein interaction modeling, drug delivery system, polymer sensor, biodegradable polymer degradation enzyme, polymerization catalyst docking. So is as much as possible, I took my time to provide some research applications of computational chemistry. So you won't just see that is a dry science. It's not a dry area. There are lots. There are a lot to it. There are a lot to it. So we have industrial. I will share this slide with you. We have green chemistry. We have nanochemistry, research applications. We have toxicological chemistry, research applications. So I'll just share it with you at the end of the session so you can read, you can look at research areas where you can exploit. Supramolecular chemistry. This is where some guys now in US are focusing on. Some guys in India and Europe, they are doing some work now on supramolecular chemistry. So it's that is a complex structure chemistry. So that is where they are. You can do a work on petrochemistry. You can do a lot of things on petrochemistry. Material chemistry is there. You apply it on material chemistry. Forensic chemistry. There are a lot of things to do. Radiochemistry. We have applications in radiochemistry. We have applications in electrochemistry. We have applications in photochemistry. We have applications in photochemistry. We have applications in geochemistry. So these are what you can do in geochemistry using a computational chemistry. We have the atmospheric chemistry. This may sound new, somehow new to us, but yeah, there is atmospheric chemistry. So to our chemists in the house, you can explore it now. Then to those in chemistry related field, we are all the same. Marine chemistry. That is the chemistry of the witches and wizards. So you can exploit natural aquatic bodies. You can use them for some chemical work. So these are some of the research applications that we have seen in chemistry. So you can exploit these areas in computational chemistry. So at least I've used our first 1 hour. I've used our first 1 hour to expose us to computational chemistry. It's so interesting. Yeah, it's so interesting. So in the next 1 hour, hands on. Tomorrow, hands on. Saturday, hands on. Okay. Question before I proceed. Abiodun, Professor Abiodun.
Yeah, thank you, sir, Dr. Henry. So, in
Thank
fact,
you.
we are so grateful, sir. Can you hear me, sir?
Yeah, I can hear you.
Yes, I want to appreciate you firstly for always being there for us, for this eye-opening presentation all the times. And we believe that God will always reward you and expand your knowledge, sir.
Amen.
Because it's as if we are paying little and we are getting more. In fact, God bless you, sir. My
Amen.
question is that all this area, in fact, I was just smiling looking at the area. Even I'm even writing them down up to the last one, marine chemistry, number 25. In fact,
Yeah,
sir, I'm so happy, sir. So I just want to beg, sir, in some
yeah.
of this area, if there are some that you've worked on before, I want to request for probably some material or journal for us to go through so that we understand it more, to know where to venture into, sir. Thank you, sir. That's my request, sir.
Yes.
Please, I have a question too.
Okay.
In addition to what the last person said,
Yeah.
my own is just a plea. I know how much I've gained. I just want to plead that you should space out these trainings because for some of us, there's no rest. If you can space them out so that we will finish one and be able to submit our assignment before another one, because we are joining this with our normal life. We are joining it with work, with all kinds of things. So, like the last assignment, in fact, it was to submit, the deadlines. So if you can space them out a bit, so that it will make time for our normal 9 to 5 jobs and things like that. It's
Chai.
just a play because the things what you are like for me, what you are teaching us is new and it's making a big difference, and I don't want to miss out. So just consider. I don't know, but if I'm the only one that is thinking like that, then you will go with the majority.
You're
Not
not the
only
only
you,
one.
ma.
The only one.
Chai.
You should look into it, I beg. You should look into it.
Uh,
Honestly, we are
ah,
just busy trying to meet up. There's a whole lot.
I don't know what to say now, but hey, well,
Most persons here actually face a lot of responsibilities.
the the thing there is that
Just
in
relax and
Hendeb
work.
this year,
Just relax and work on it and get back to us.
in Hendeb this year, we 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 had a rushed decision that at least in a month we must run up to 4 to 5 trainings, and and almost all of you want to participate in all this training. So it will become very problematic because we want to participate, and so and that will we that will choke most of us. Hmm.
You can just
But please,
you can just think about it.
It's already
Just think about
choking now.
It's choking. You can just think about it, please, and
well,
whatever you decide.
why, why won't you skip some of the training? You must not join all the training.
It's necessary now.
It's necessary because they are, they are. It's like from one step to another, and all of them.
All the training are related.
That's what I want to say. They are related. Yes,
They are all
they are,
related.
they are
If you
related.
skip one, you will miss. You will not even know how to continue with the other ones. So please,
Don't
maybe 1 month training, the other month we use it for the assignment. Then the training should continue the 3rd month. If it's possible, we are so choked.
half-baked knowledge is
Okay,
not needed.
well, I'm not alone, so we'll consider it.
Okay, sir.
We'll consider
Thank
it,
you
but
so much, sir.
we'll put it into consideration, and let's see how it goes. Then, yes, there is a very important point Abiodun raised concerning if we can share some of our publications on these areas. I'm sorry to say this, but I've said it before. Most persons have come to my DM asking for such publications. If for those of you that follow me on LinkedIn, there's some posts I do make, and those posts is actually kicking against publication. And I have said it here in some of our training that this ideology of publication is not my thing. In the newly released this month, they released a list of top 500 researchers in Nigeria. The number one was a group, in fact, is my mentor, the immediate past president of Nigeria Bioinformatics Network, Professor Charles. He is the director of research in Edo State University. Now, I look at other people who are there. These people doesn't have a patent. They don't have patent. They don't have product that they are patented. But they have research paper that have been published. So in Hendeb, we took our time to say that we are not after publications. We do research, like we do so many research, but our research is not towards publication. All our research is towards production, towards products. So all the work we are doing, we are developing prototype that we want to come up with a product. From July, we shall be coming up with our product on biocoagulants. One of the products we have on biocoagulant for water purification. So, my dear, I don't know. The only time, because I'm not into the academic system, so that is why I'm not bothered about paper publication. That is how Nigeria has made, that is how Africa, and in fact, the world has made our academic system that your promotion, your ranking, your respect, authority in that field is proportional to your number of paper you have published. But that is nonsense. How many products have you developed? Have you patented? That is what I'm really after. The outcome of this your research work. Let's have a prototype. So the only time you see my name on any publication is probably I did a work for somebody. We did a work for somebody, and the person decided to include our name as the co-author. So that's the only way you see our publication. So maybe I will search some of this work I've done for people that they have published and share them with you. But for our work, no. We keep it for ourselves and for product formulation. So I'm really sorry, but that is our mandate in Hendeb. We move from training to project to paper and then to product. And that is why in Hendeb we have 4 units. We have a unit for training, which is the School of Computational Chemistry and Biology. We have a unit for research, that is the Hendeb Research Institute. We have a unit for lab work, that is a Hendeb Biophychem Laboratory, so they're in charge of all lab work. We have a unit for product formulation, and that unit is a Hendeb Pharmaceutical and Allied Products. So that they are doing a lot of work on prototype, chemotype development. So, but we search for some of the work that I've done with some people and share with you. So that is all what I can say for our job. Okay. Thank you so much. Sorry, our own ideology somehow. So, but I don't know. Maybe God will help us, yeah. Okay. So at this point in time, okay. Aina Oluwatoyin, your hand is up.
Yes, just based on the installation of the ChemDraw, I'm still having challenge. But this time it's just saying runtime error 339. Then said there's a component that is missing. The file is missing or invalid. I don't know why.
This one now, I don't know what I will say in that one because I have not encountered that challenge. Okay, so what I will do.
Okay.
I have classes tomorrow from morning to 2 p.m. Okay, for all of you who have challenge, except this would have challenge on installing NetFrame 2.0. I've sent on the WhatsApp platform your solution. So if you have any other challenge apart from that, screenshot it and send to my DM.
Okay.
So I will just give you instruction on how to follow it up.
Okay.
But that will not stop our hands-on tonight. So we shall still have the hands-on. The next 1 hour, we shall look at a little hands-on. So we may be dismissing by 10 minutes after 10. So the next 1 hour, let's see what we can do. Let's see what we can do in next 1 hour. So those of you who have installed your system, just open up your ChemDraw. So I will show you how to do that now. All right. So somebody is asking, is ChemDraw different from ChemSketch? Yes, they are not the same. They do similar job. They are all structural chemistry softwares. They are all structural chemistry software, but they do different job. Their jobs are different. There are some things ChemSketch can do. Like ChemSketch can calculate reaction mechanism, but ChemDraw cannot calculate reaction mechanism. So as we continue, I will show you some of the things ChemSketch can do, the one ChemDraw can do, and ChemDraw. Well, in overall, I recommend the use of ChemDraw. I recommend the use of ChemDraw. So let me share my screen. So we see what we have. So whether it's coming, let me open up our module. Let me open up our module so we know what we have to cover and what we have covered. All right, so those of you who have installed ChemDraw, once you install ChemDraw, it comes with Chem 3D. So once you install ChemDraw, it comes with Chem 3D. So Chem 3D comes together with ChemDraw. So today we have done with the basics of computational chemistry. We shall look at modeling of chemical structures. So drawing of chemical structures. Then tomorrow we'll look at chemical identity and modeling. While on Saturday shall be given to analog generation, minimization, and optimization. So let's look at drawing.
Okay, so the training is ending by Saturday, right? Or
Yes,
is
yes.
Saturday? Okay.
Today, tomorrow, and Saturday.
Okay, sir.
Yeah. So it will not interfere with our Friday class for those in macrognosy. So just type ChemDraw. Once you search ChemDraw, it will open. So this is ChemDraw Ultra. You double click, and this the software we open. So we will be using it while that is opening. I will walk you through the environment of ChemDraw. We shall see. We'll just look at the environment and do some introduction to ChemDraw. There are some persons here who have used ChemDraw before, so I think they will even help me to make the job faster. But I will not be fast because this is beginner's class, so I will not be that fast. I will just take my time to make sure you grab it. All right, can you see my screen?
Yes, sir.
Okay, and I believe that some persons too who have installed it, their screen is like my own. So this white space,
Yes, sir.
yeah. So this white space here is called canvas. It's called canvas. Just like we have documents in Microsoft Word, we have workbook in Excel. So this white space is called canvas. That is where we do all our drawing. Now these tools here, they are structural tools. They are tools that we can easily access to work with. Some of them are found in each of these menu bars. Some of them are found in each of these menu bars. So it's very simple. It looks so simple, not as complex as a ChemSketch is, but it's so simple and it's very good. So I will walk you through these tools here now. Most important tools here. Starting with this one. Can you see my screen? My cursor? I will be getting response from you now. It will be better, please.
Yes, sir. Yes, sir.
All right. Solid bond. Solid bond. Solid bond.
Okay, solid bond. Okay.
Yeah, my cursor is. So we can use it for if you want to draw any bond. So you just click it. If you click it, you paste. So if you want to draw any kind of structure, you just be using it. Just anywhere you click on it, it will draw whatever you want to draw. That is what that one is. So even if you want to draw double bond now, once you have chosen that solid bond, if you click on a single bond, let me zoom my page so that what I'm doing will be very clear. All right. So I think this is better now, right?
Yes.
So what I'm saying is the solid bond. Once you click on the solid bond, you can use the solid bond to draw structures.
Sir, please, the solid bond, is it the black box?
Yes, here my cursor is. See my cursor?
All right, sir.
Beside eraser, yes. So anywhere you click on it, it will draw a dash bond, a bond. Now, if you want to draw double bond, that means that place that has a single bond. Once you take your cursor to that single bond, click on the single bond, it becomes double bond. And if you want to draw a triple bond, the place that has a double bond, click on it also. It should become a triple. Let me see. Okay, it's not coming up. Now I will give you how to do that. The triple bond. Sorry. Okay. All right, I will show you that. Just all right. So don't worry, I just did something. So if you want to draw bond, that is use the solid bond to be drawing your bonds. So any structure you want to draw, use the solid bond to be doing that. Now, I think I would have just taken it serially. So let me just take serially. You look at this. There are some I will strip and that are not necessary for beginning. So look at this first one now is Matthew. That one is Matthew. The Matthew is used to select. So once you click on the Matthew, you can use it to select structures. You can use it to select structures. So once you just click on the Matthew, if you want to select a structure, you click on the Matthew, and it will enable you to now highlight the structure you want to highlight. Just click on the Matthew, and that is how that works. So even if you have multiple structures, that one you want to highlight, you make sure you click on Matthew, then take this box and hold your left mouse, then drag to cover the one you want to highlight. Now you can do that using lasso. Beside the Matthew is lasso. Beside this Matthew is lasso. Lasso does not draw. If you watch the Matthew can draw a rectangle box around your structure. So you select your structure by drawing a rectangular box. But lasso draws. Yeah, you have a question?
No, sir, I was not seeing it before. That's why.
Okay. Lasso is beside the Matthew. What lasso does is still selection, but it selects by drawing by just making a curved drawing around your object you want to select. So that is how the lasso works. So I use lasso when I have clustered objects, clustered molecules, in the sense that if I'm trying to use my Matthew, trying to draw this box diagram might interfere with other structure. Like, let me show you something. If I want to do this, if I place this structure here now, and I want to just highlight the first one, if you're using last Matthew, there's no way you can only highlight only the first one. So you see that since you're working with boss with the last Matthew with boss, you cannot maneuver highlighting only the first one. You end up covering everything. But since I want to just highlight the first one, I will use my lasso. I will just use my lasso and just make the drawing around the first one and it will only highlight the first one, so you can see it. So that is the usefulness where I love using my lasso. So you know when to use your mark cube for selection. I know when to use your lasso for selection. All right. The next one here is fragmentation tools. So I may not go into this for now, maybe later, but we use it if you are studying MS, yes, mass spectrometer. You know, MS operate based on fragmentation into base speed, ion speed, molecular speed, and all that. So we use that to show fragments, but that will be later. Below, I'm just walking through this line. So I'm walking through the first line now. Below is your eraser tool. So if you want to erase, you can click on the eraser tool, come to where you want to erase and click. So it will help you erase whatever you want to erase. Just giving the basic foundations. So are we together?
Yes, sir.
Yes,
All right,
sir.
thank you.
Yes, sir.
Below the eraser tool is your test tool. You know, when we use ChemSketch, you have some functional groups there. You can just pick and paste. But in ChemDraw, you do everything by yourself. Oh. So this letter A now is for test. Anything you want to write, both atoms. If you want to type atoms, if you want to type anything you want to type, you use it for typing, for test. That is what it does. So let's take, for instance, now I want to include maybe I have a bond here and I want here to be OH. So if I want this place to be a OH, I will pick my test and type the OH I want here to appear. So you can use capital letter. So once I have done this, the system will now recognize that there is OH functional group. The same way you used to use your pen and paper to draw the OH on the paper. So you immediately put OH. What is there now is now a hydroxy group. The same way, even if I'm using ordinary test, it will just recognize that what is there is a hydroxy group. So any atom, any functional group atom you want to type, you use your test, the test to type it. And one thing about this is that the bond length are uniform. Though you can increase the bond length, I will show you that later, but the bond length are uniform. So you will not have a case whereby one length is, you see that if you try to make the length longer, it's not possible. Even if you want to try to extend drawing the length, the bond length is just uniform. So, but that is by the way. Then below it is pen tools. We may not necessarily need this now. It's not necessary for us, but where you use this is if you want to draw reaction mechanism, but that is not necessary for this course. What is very important is the arrow tools. And please, if you look at each of them, you will see this black drop down, this black arrow at each edge. I don't know if you can see it in your own.
Yes, sir.
Yes.
Yeah. So what I
It's
mean
there.
is that what I nice is that there are other tools inside. So for you to see those other tools, just maybe point at this one and hold your left mouse. So when you point at each one, you hold your left mouse. Once you hold your left mouse, you see others inside. Can you try it?
Yes, sir. We've seen it.
So once you hold your left mouse, it will open you others that are inside. So we are on this arrow tools now. These arrow tools, if you are doing reaction mechanism now, if you want to show how you want to show the full head, the half head, if you want to show the directional arrow, so it all depends on what you want to do. If you want to show reversible reaction, if you want to show a product arrow pointing towards the product side, so that is where we use this arrow for. That is the arrow, so you can exploit from there. This one below is for orbiters. It's not necessary for us. It's for orbiters. So that may not be very much necessary for us. Okay. So I'm just going serially. I'm going serially. All right. Then if you look the next one down, the next one down is drawing tools. We also may not need these drawing tools. It's still similar to arrow tools. So it's still based on what you want to do. Even the same thing, the next one down, bracket tools. Okay, these bracket tools, you can use them, especially maybe you want to show for those in polymer chemistry, you want to show a polymer, so you can use that. Like for instance, I can use this one now, this first one, to show that this compound, this is a polymer. So once I do like this, then I take my atom, come down and type N. So if I type N below, what I just did is I just indicated that is a polymer. That is a polymer. So it all depends on what you want to do with it. This is brackets and others. Another important tools I want to show you is the chemical symbol tools below. Now, this is very important. This is very important. If you want to represent radicals, you want to represent charged carbons, you want to represent maybe a chain. Let me show you something. Like if I draw this, I'm coming, and I have this. Now, if I want this single bond to be anything, if I want to show that this single bond can be any functional group or any structure, I'll make use of this wave here. Once I click on that wave and draw it here. So once you click on that wave and draw it here, it's supposed to come up. Come in. I'm coming. That wave is to indicate that, okay, that the structure can appear anywhere. It's supposed to respond. I don't know why. Let me show you if we can use it. Okay. All right. So to use it, you just pick it, click at the terminal atom. Now, this will mean that any structure can come in here in place of this single bond. It can be NH2, it can be OOH, it can be anything. That is what this wavy bond means. Mostly those who are building a optimization, those who are doing optimization, who are building analogs. So you can exploit that principle. You must have seen, most of you must have seen that in some structures where you see this wavy stuff. Then if you look inside that same spot, you will see this first one showing plus. So let's say, for instance, you want to show that this carbon is a positive carbon. You use your plus to show that it's a positive carbon. If you want to indicate that the carbon is negative, you use the minus. The minus will help you and to show that this carbon is a negative carbon. So whichever this one comes in, if you are doing if you are showing reaction mechanism, where you show the bond breaking and bond formation, for those who have little understanding on bond breaking, bond cleavage. So you use that to show the bond cleavage, how the electrophiles and nucleophiles are generated. Where you need to put ions, you use that to show. Then where you need to put radicals, if you want the normal plus, you can also pick the normal plus. You can still choose the normal plus and click on where you want it to appear. It will show plus, or you want the plus in a circle, or just the normal plus. So you can exploit on it. There are many things you can exploit there. If you want to show radicals, yes, there are radicals. You choose for radicals. That is dot. You know, the dot is your radical. So that is one major thing you can do from these chemical symbols. Yes. So I'm just taking you through the environment. I'm taking you through the environment, and that is very important. The query tools is not necessary for us. These advanced tools, they are not necessary for us. Even this one is not necessary, but where you may use this one is for templates. So that is for templates. Okay, this one now is for templates. Very important. You can use that to get templates. Templates are already designed structure. Already designed structure. So that is your template, already designed structure. You can easily use them. If you come to amino acid, these are some already done amino acid structure which you can use easily to speed up your work. If you come to aromatic, these are some aromatic structures. Please, are we together?
Yes, sir, we are together, sir.
So if you come under aromatic, that's some aromatic. So you can easily pick up these, easily pick them and do your drawing if you want to work with them. If you don't want to stress yourself in drawing those structures, you can come to the template tools. Under aromatic, you can pick any one of your choice. Then under bicycle, depending on your boat shapes, under clipper wear part 1. Now, clipper wear part 1 and 2 is for laboratory setup. You can just use this to show a little laboratory setup. You can use this to show a little laboratory setup, but that is not our scope. We are just giving you beginner course. Yes, I think is a step at a time. Then we have conformers. If you want to show your conformers, depending all this your glucose shape, your bolts and shear structures, and you can use this. And so on your own, exploit this template. Exploit the templates. They are very important. Then apart from the template, now if you come down, there are some structures, some easy to use structure that is here. There are some easy to use structures that are here. This is cyclobutane. So if you want to draw cyclobutane, you can just click on this one and paste it to show you your cyclobutane. This is cyclohexane. You can click on cyclohexane and paste, so it will easily bring up cyclohexane. Then this is a cyclohexane, but the shear format. So that is what that one is.
Sorry, sir.
Yeah. Yeah, I can hear you. Can you hear me? Okay. Maybe that should be network
Yes.
from.
Yes. Can
Okay, go
you?
ahead.
So how will so I want to ask, how were you able to make your my own is not
Okay.
standing the template?
Once you can get it easily. If that one is stressful, you can get it easily. Go to view. Go to view. You see templates.
Yeah.
Go to view. You see templates.
Okay, I think template, yes.
So whichever one you
Okay.
want, you just click on it and you see them.
Okay.
Yeah.
All right. Thank you, sir.
Yeah.
Yeah, I've seen it. Thank you, sir.
But if you still want to exploit from here, once you click on that black dot, hold your left mouse. They will open. Once you click on that black dot, hold your left mouse, they will open. Then you use the other finger to navigate around them. But you must hold your left mouse.
Okay, yes, it did. It worked.
All right, thank you.
Thank
So
you,
this
sir.
is benzene. Yeah, you're welcome. So this is benzene. If you want to draw a benzene structure, you can quickly pick up benzene and paste. Okay. Beside benzene is a cyclopentadiene. So if you want to draw something that looks like this, you can pick it. You can even pick it and attach to this benzene if you want. So you can attach it to benzene. What you just do is, if you want to attach any structure to benzene, pick that structure. Maybe I want to draw two benzene. So once I pick this one, if I want to attach it to the other benzene, just take your cursor to where you want to attach it. Click, touch the bond where you want to attach and click. It will bring up the other structure. So that is, if you want to attach two structures together, you must click on the one you want to attach, then go close to the bond, that boundary, the bond where you want the other structure to get attached to. Click on that bond, then it will attach at that point. That is one good thing about joining structures together. All right. After the cyclopentadiene, above is also a chair of cyclohexane. So up is still cyclopentane that we have discussed. If you go up is a cyclopentane ring. This one is just normal 5-side ring. So if there's a need for it, you can also use it for your work. So you see that they become so easy. They become so easy. This one is cyclopropane. So if you need cyclopropane, you can easily get that also for your work. Can get that for your work. All right, so now this is chain structure. I want to explain something here. I'm going to explain how to use this chain structure. So I'm just showing you the tools which you can use to navigate drawing of structures. So I'm just showing you the tools you should use to navigate drawing of structures. So this one now
Can you hear
is
me? Hello?
yeah, yes.
I get how you did that wavy bond stuff. I've been trying it since. I don't seem to get it. That wavy bond
Okay.
stuff on that benzene ring.
The UV bond, you draw benzene. I just showed you. If you want to use the UV bond, just click on the UV bond. Where is the bond? Okay. So click on this UV bond and then click the atom where you want it to appear. But you can use a single bond. I use a single bond to show that. Then if I click on this UV bond, then come to this atom where you want that UV bond to appear and click. Now, but there's another UV bond too. There's another UV bond. Look at here. Can you see my cursor? This is UV bond with a terminal arrow, and there is a UV bond without a terminal arrow. So if you want to use this UV bond without a terminal arrow, you don't need to click at the terminal. You just need to click on it and come to anywhere you want it to be and draw it. So that is it. So this one without arrow does not need a terminal chain. So in fact, the one without arrow is mostly used. It's mostly used in research. Maybe I drew benzene and I want to attach unknown atom to this benzene. So if I want to indicate that I want unknown atoms to be in this benzene, maybe I have multiple alkyl, multiple side chain that I want to attach to my benzene. I'll just use this wavy bond, the one without a bond. Just click on this one and come to this place, shift a bit, then drag it. So this simply implies that there is a wavy bond at that point. This means that at this single bond here can be anything. So that is what implies, in case we come across it in chemistry, in case we come across it in some studies. So is that okay now?
Yes, sir.
All right. I was trying to explain this chain tools. We use these chain tools to draw multiple chain. There are 2 in number. We have the one that is thread chain and weavy chain. Let's say I want to draw cyclo structures. I want to draw cyclos. So that is where we employ this weavy chain. So if I click on this one now, the one I click, I can use it to form a cyclo. Sorry, let me show you. There are 2 weavy chain there, one with just straight and one with a curve. So if you're using the one with curve, you can use it to form complex. You can use it to form cyclo chains. So you can use it to form a cyclo chain. So if you want to draw cyclo, now even if you want to draw If you want to draw is not 5, maybe 6, any shape at all, you can use it as much as possible as you can. Now, but there's something I want to show you. There are some structures that are very complex. So I can draw a chain that has up to 15 to 17 sides using this weaving stretch chain. You just have to just maintain the number you want to draw, like 23, 24 cyclo chains. You just have to maintain the number you want to draw. So that's the beauty of this weaving bond side chain. You can draw multiple side chain, but the one that is straight, this other one now, this one is just to draw straight line. But you can now convert, after drawing this straight chain, you can convert this straight chain now to a cyclo chain. So let me show you how to convert a straight chain to a cyclo chain. Like if I draw this straight chain, I can make it a cyclo chain. What you do is, can we do that together? How to draw cyclo chains using this straight chain. Can we do that together? For those that have their system, their ChemDraw with them. If you want to draw side chain as if you want to draw cyclos using this straight chain, click on this straight chain. Then how many chain do you want? You hold your left mouse and drag, keep dragging, you keep going. Probably to this extent. Then click on your mark Q. When you click on mark Q, click outside. Because once you click on mark Q, it will be selected. Click outside. When you click outside, then go to the first atom here. Hold your left mouse, drag it to the last atom. Let me go back again. See what I did. If you want to draw a cyclo chain using these chain tools, click on that chain tools. Draw as much depending on the number of chain you want. After you have done that, click on your mark Q. That is the select tool. Mark Q is your select tool. Once you click on mark Q, then it will select that structure. Click outside so that the structure will not show that it has been selected. Once you click outside, then take your cursor to the terminal atom. It will show color blue. It will show that blue dot. Hold your left mouse. Once you hold the left mouse, drag it to the end, to the last terminal. Then if you have done that, you click on clean structure. You click on clean structure. So this is clean structure. Come to structure. It should appear. Okay. Clean up structure should have appeared. Okay. All right. So clean up structure. There's an error somewhere. The structure would have cleaned up and clean up structure. All right. Okay. So let's do it again. Let's do it again because some structures you'll be encountering those stuffs. Click on the side chain to depending on the number of chain you want to draw. That's this is how many chain here: 1, 2, 3, 4, 5, 6. So if you are drawing it, if the number stops at this 11 means 10 chain. So if I stop at 7, 7 means 6 chains. So 7 means 6 chains. So what you will do is click on Matthew. It will show selected. Click outside. Then take your cursor to this first terminal. It will show blue. Hold the left mouse. Once it's showing blue, hold the left mouse and drag to the last terminal. Then, having done that, select the structure. So go back to Matthew and select the structure. So once you select the structure, you go to structure and click on clean up structure. So once you click clean up structure, it will turn to a cyclo structure. Is that difficult to do? Hello?
Yeah, we got it. You got it.
All right. So that is the benefit where you can draw multiple cyclo structures. The other one above it is not necessary. I've explained the wavy bond. Then these are stereo bonds. So these are stereo bonds. It all depends on how you want to represent your structure. So these are stereo bonds. All those are stereo bonds. So maybe I want to apply. So if I want to apply the stereo bond, you just click on the bond. You just have to click on the bond and go to where you want to apply the bond. So probably this one. If I want it to be here, I click here. You can alter it by clicking. It will be changing the direction. If I choose this one, anywhere I want it to be, you can alter it. It will be changing the direction. If you want this one, the bold one, anywhere I want it to appear, they are just stereo bonds. So they are stereo bonds. So all right. Then these are hashed wedged bond. So probably if I have an external bond here, and I want it to show that wavy bond, that wedged, I can click on this one and click on it. It will turn to a wedge. You can change the direction of the wedge bond depending on what you want to draw to show stereomerism. There's another one up. You can also click that one to change to different formats. So it all depends on what you want. Then the up here is multiple bond. Up is multiple bond. So you can show multiple bond. So there is triple bond, double bond, and different kinds of multiple bond that you may want to show in your story. So if I want to have a triple bond here, if I want this bond to be triple bond, but if I want double, once I click on it, it will become double. Yes, but if I really want a triple bond, let's say I want a triple bond. I want to have a triple bond. So once I click on a single bond, it will become double. But if I want to have a triple bond, then I will go to this multiple bond, open it up, choose triple bond. This is triple bond. Once I choose it, I will come back to this place and click. It will become triple. to now become triple. That is triple bond. Then the last one I have not explained is this. That is structure perspective. You can use it for rotation, to rotate your structure. You can use it to change the mirror. You can use it to change the mirror image of your structure. Whichever way you want to keep it, that is structure perspective. Now, I want to show you about rotation. You can use your mark to rotate. Like if I want to rotate this, my structure here, anyone, I click on the mark and I select it. Then you see this external, there is this edge, this external edge here, this line coming up. I can use it to rotate it. So once I take my cursor towards that edge, you see that it will show an arrow. It will show this directional arrow. So just give me a few minutes. I'm coming. Okay, so I just have to try to put on my power, my plan too. All right, let's continue. So what I'm trying to say is you can now rotate using that rotation. Once you once you are able to use your mark with your mark you select the structure or select structure. Okay, so you select the structure with your mark then it will show you this this point, this extended arrow. So once you take your cursor towards that point, it should to turn to an arrow. It will turn to an arrow towards the direction you want. So you can turn towards any direction of your choice. So this is a basic way you can use that arrow. You know, hold your left mouse and rotate to how you want it to be. All right. So that is for that. Then if you don't want your benzene to be like this, you know, this is benzene, but this is also another form. I'm coming. there's something I need to show you. All right, so you see, these two structures are not the same. So most times you may want to draw this type of benzene, right? So how do you do that? Is a very simple thing. It's a very simple approach. What you do is pick your benzene, but once you pick that benzene, don't paste yet. Don't paste yet. So once you pick your benzene, it will show you benzene. Press Control. If you look at my cursor, once I pick benzene and then I click Control, something is changing. The cursor is changing. If you carefully look at the cursor, once I press Control, it will show cyclo inside. Then click OK. Then it will now show the resonance structure of benzene. So I'm just taking you through the environment and some of the things that you may need to know before we start drawing structures. So do you have a question to ask?
Sorry, sir. I didn't see how you made that cycle in that benzene ring.
When you click on the benzene, when you pick your
Yes.
benzene, if you click the
Yes, sir.
benzene, don't paste yet. Then click Control, hold Control key. Once you hold your Control key, it will show in your
Yes, sir.
cursor a circle. Then click. Have you tried it?
You said to show my cursor.
What I said is, when you click on your benzene,
Yes.
your cursor will be showing
I've clicked on
benzene now.
benzene.
Yes. So
Yes.
your cursor is showing benzene, normal benzene.
Yeah.
Press
Yes.
Control, hold Control key.
Yes, sir.
Now, each time you press Control, look at the cursor, something is changing. If you hold Control key, it will now show you a circle inside that benzene.
Yes, sir.
Then click where you want it to be. It will show your cyclo, your resonance structure. Have you done it?
It's still coming out as the triple double bond, the conjugate double bond.
Don't remove your hand from Control. Your hand will be in the Control.
Okay.
Once you click on benzene, then hold your hand in Control. Just keep your hand in the Control. Don't move your hand.
Yes, I've done it.
Okay, all right.
Yeah, thank you, sir.
Yeah, welcome. All right. I don't know how we give you assignment now because we are meeting tomorrow, but I won't give you assignment. But I'll just ask you, look at any structure and see how you can draw it. See how you can maneuver what is here to draw them. If you have free time, any of your free time tomorrow, probably tonight before you sleep, because even me, I'm not going to bed right now, so I still have a lot of things to do. So I'm not also expecting you to go to bed now, but people who have stressed themselves, we need to go and rest for tomorrow's job. It's not easy. It's really not easy. I discovered that some of us usually battle with this class itself. Maybe due to stress, immediately you come back, you result join the class. After 30 minutes, you start obey. You begin to obey the natural call. You start battling with natural call. You sleep and wake up, and you hear voices. Click on this and this. You go back again and doze up and continue. It's normal, but I really appreciate your effort. So tonight I've been able to take you through the basic tools. In file, There is no much thing in file. What you find here is how to just to save, open, close. In edit, what you can see in edit is very important. Is if you want to generate smart code of any structure, you come to edit to do that. So if you want to generate smart code of any structure, you come to edit. You come to edit to generate that smart code. So that's what you can do in edit. Like if I want to generate smart code now, maybe I want to generate a smart code for this structure. Let me see. For this structure, I need a smart code for this structure. Come in. Let me just select one down. Okay, maybe for this one in particular, if I need a smart code for this structure, let me use my macro. Let me just select this one. So if I need smart code for this structure, once I select the structure, I will go to edit. In edit, you see copy as. You see copy as, then click on smiles. Smiles. So smiles will generate the structure. It has been generated. You do Ctrl V to paste it. You drag it to where you want to place it. So that is the beauty of generating smiles. Very important. You go to edit and this copy as. You see smiles. So most of the things we have done are these tools. All these tools are most of the things we have touched. Then in objects, you can change your fixed length and fixed angle. Not really necessary for us now. Then as I end discussion tonight, you can use ChemDraw to generate name of your structure. I can use it to convert your name to structure and your structure to name. So if you look at structure, you will see convert name to structure and convert structure to name. Okay, are we together?
Yes, sir.
Yes, sir.
So if you have a name, you want to get the structure, just go to structure, choose convert name to structure, then type the name of the compound. Let's say ibuprofen. I don't know the structure of ibuprofen. Preferably use the IUPAC name, but the common name can still go. Once you type OK, it generates for you the structure of ibuprofen. So this is the structure of ibuprofen. Okay. And also, let's say I have the structure, but I don't know the name. So you can select the structure the same way you can select the structure and generate name for that structure. So, this was the part of the limitation we had in ChemDraw, in ChemSketch, that the ChemSketch was unable to generate name for large structure. So irrespective of the structure, ChemDraw will generate the name. So since you have selected the structure, you go to structure, you say convert my structure to name. It will give you the IUPAC name, which is 2,4-isobutylphenyl propanoic acid. So even if you take this name now back, it will still give you back the structure. So you can convert your structure to name. You can convert your name to structure. Maybe you encounter the name of a name somewhere and you want to know what structure could that be? Just take that name to ChemDraw, paste the name, it will generate the structure. And also, you are given a structure and you have to find the name of that structure. Just come to ChemDraw, draw the structure that you have, go to structure and generate the name for that your structure. That is one beautiful thing about ChemDraw. So we have succeeded tonight in doing something from basics to drawing of structures. I've taken you through the most environment. Yes.
Please, where did you get the name?
Which of the name?
You said when you draw a structure, you can name it. Okay, convert structure to name.
Okay, to convert structure to name, right?
Okay, that structure. Okay.
Yeah. There are two options there at the end. We have convert name to structure. That one is you have a name, just type the name and say, okay, it will bring up the structure. Why the other one? You have the structure, you have the structure you have drawn, you want to get the name of the structure. So you select this, you draw the structure, select it, come to this place and say convert structure to name to now bring up the name of that structure.
Okay. And then secondly, is it all structure that has a smile?
Yes, all structure has a smile code. Smile code is part of your chemical identity.
Okay, because I picked this cycloheptane and tried to do what you did. There's no smile code is coming up.
No, you did not paste the smile code. After you click on smile code, it has copied it. Then press Ctrl V. Once you press Ctrl V,
but mannequin is not picking it too.
You say?
The mannequin did not pick it. The mark.
Let me see.
Did not.
Let me see what I say. You let me pick cyclo this one now. Once you have it, I want to generate the smile code for this. I will select it. I will click on Matthew. Once I click Matthew, it has been selected. I will go to edit. You see, copy. So I have copied. Once I click smiles, I have copied the smiles. I have to paste it because I copied it. So in pasting it, I'll say Ctrl V.
Copy first.
Yes, copy as. Go to edit now. You will see copy as.
Yes.
Copy as.
Yes.
Under copy as, you see smiles.
Yes.
Once you click on smiles, that means I have copied the smiles for this compound. I need to paste it now. So Ctrl V. Ctrl V will now paste the smiles.
It doesn't appear automatically. Okay.
No, it doesn't because it's copy. Yeah.
Okay. All right. Yeah. Thank you, sir. That was where I was missing it up.
All right.
Thank you, sir.
Yeah, welcome.
Then the coil, it doesn't, when I'm trying to put it at the middle, it's always coming at the edge.
Which are the coil?
That coil chain, coil, that's for cleavage.
For cleavage. Is it the one you used to draw cyclo
wavy bond.
Okay, wavy bond.
Yes.
Okay, yes. What is the challenge?
Each time I try to put it on maybe on an archive group, it's not staying in the middle, it stays at the edge.
Is it something similar to what is on my slide, like my screen now?
Like what you are doing now. If I want to do it, it's always the edge I can pick it up. Yes, like what you are doing now is centralized on the
Yes.
wavy bond. I want to be able to put it here on a centralized, just the way you are doing it. My own only comes at the edge, at the tails.
Pick this wavy bond. There are two here. Pick the one without a bond. This wavy one. This wavy one. This one without a bond. Look at my cursor. Use that one.
Yes. I don't even have anyone that has that. I picked it.
So go to where you want it to be and draw it. Drag to that point. You have to just use your hand and design starting from here to here.
Okay.
Okay. So you use your hand and said, I want to draw from here to this place. From here to this place. So you just you drag and put where you want to. So don't just click. If you take it, don't just click. Don't just click. It's dragging. You drag to like now.
Yeah, I've gotten it. I just.
All right. Thank you.
Thank you, sir. Yes, sir.
Thank you. All right.
Hello,
Is it yes?
Hello, sir.
Yeah, I can hear you.
Sir, can you hear me? Yeah.
Yes, I can hear you.
So when I click on chain tools, it will ask me how many chains do I want to draw.
On the chain tools?
Yeah, when I click on it, it will ask me how many chains do I want to draw. Like if I put 5, if I like open chain, that is how it will generate like 5. If I want 5, if I want 4. So I don't know why it is showing me like that. But after I click 5, it will draw it automatically.
Yes, same here.
That was also how I did my own too. Shortcut.
Then you want to draw and say, okay.
Hello?
Yes?
Yeah, I said, sir, when I click on chain tools, it will ask me how many chains do I have, do I want to draw.
Yes, you can now type in the number of chain you want to draw.
Okay.
And click OK. It will bring up the chain for you. Still the same thing.
Okay, but in your own case, it's not showing you like that, sir.
I wouldn't know why that one is happening in your own. Well,
Maybe it's different version. Different version.
But just try this way that I told you. Try it and get, but just do it now. Is it something like this? Is it this thing you're saying?
Yes.
It depends on the way you operated on it. I understand. So like now, let me say 18 chain. Let me put my own 18 chain and I say add. So you just see that it will bring up the 18 chains for me. So if it happens that way, there's no problem. You don't have a problem with it.
Okay.
Yes.
Okay, so does that mean if I draw like 20, 30 structures, I can save it like in the file? If I click on file, I can save it in either Word document or PDF file.
Yes, there are different file formats for saving. That is which I will carefully look at that tomorrow. Okay. When you come to saving, there are different file formats for saving. We have we have most of the important one here is SDF. We have SDF here, the mold file. There is MDL SDF file. So that same format we do download from PubChem. So is here. I will take my time to look at it tomorrow. So what we'll do tomorrow is to model some of the structures. Yes.
Okay. So when I highlight my structure that is using my key. And if I click on edit, and if I select smile, that is if I want it to generate smile. So it is not
Yes.
generating smile.
No. What you are doing is somebody have asked that question. Once you click on it on your structure, then go to edit. When you go to copy as, right?
Okay, I should not click on my key.
No, click on smile. Like, look at it now. Like, now I click on this structure. If I want this structure, I choose this structure. Let me select it. Once I select this structure now, I go to edit. Are you following me?
Yes, sir.
Now I go to copy as. Copy as. So I want to copy smiles. I want to copy smiles. So I click on smiles. That means I have copied the smiles. It will not appear here. I just copied it.
Oh.
I have to paste it.
Oh.
So paste it by saying Ctrl V.
Okay.
Once you click Ctrl V now, it will paste. It to where you want it to be. Yes.
Okay. Thank you very much.
All right. In fact, by the time we continue, you will see that there are some structures you will draw. If you copy their smiles to PubChem, PubChem will say no, you will say structure not found, because those structures are still novel. They are not found in PubChem yet. Like, it has not been deposited in PubChem. But if you paste the smile code in ADMET, in all these ADMET the database, it will show, because those database does not work with deposited compound. They work with algorithm. But PubChem only work with what is deposited in it. So if you put something that is not found in it, it will say not found.
So how do you, if you generate a novel, if you created a generate, I mean, if you create a new O novel structure, chemical structure, how do you put it in the PubChem?
Okay. You can upload to PubChem. PubChem has that
policy.
That part where you upload your new compound, but then you don't upload direct to PubChem. You upload to the managers of PubChem, so they will need the details, other details of that compound, like the physiochemical properties, if work has been done on it, as much as possible. They will need relevant information regarding that compound. Then it will go with your name.
Okay.
Mm.
Thank you.
All right. So remember what I told us earlier, that our project is 5,000 compounds.
On God, oh.
Forgive me. There is something my students will always say. Each time I want to give assignments, they will start shouting Jesus. You know when they're shouting Jesus?
No, sir, tell us.
They know that I can't give something less. So they just know that Sahari cannot give something less. So I don't know. I cannot call 100 now as beginner, but it's very simple. I will show how to do that.
For how many years?
No. In less than just if you can give it a day, or no, 2 hours, 3 hours can do that. You can just spend 3 hours of your time and give to it. You are done with it.
Really? So,
5,000. I will show you 5,000 compounds.
How, sir? All right, sir.
5,000 compounds. Oh my God. All those things we are going to download on PubChem. Now, people will draw like you now. They draw it like this, modeled it, and upload it on PubChem. and we are going to just enjoy it. So once again I want to appreciate your time. It has been a good, brilliant class, exposing you to structural chemistry. So I want to appreciate that your time. The most important thing is the time you made available, because a lot of us are very busy. Even me too, I'm busy, but just like how some of you is asking for this thing. Some of you is asking for space of time. Even we that is handling the session, it is not easy on us now. But we keep doing it because it's a trust. It's a trust we have carried. Imagine that I teach not only in this my organization, we also anchor sessions for people. We do that every day. We run classes here in Hendeb every day, 8 p.m. to 10 p.m. every day, except on a Sunday. But like I said, we'll discuss. I will look at your plead. We'll discuss, and I will get back to us tomorrow next until when we get approval. Order approval. But once again, thank you. I want to especially somebody wanted to register, and the person said, this training is for students. I said, join, which I'm a student. So I want to appreciate Abiodun. I want to appreciate Abisoye Odofin. I want to appreciate Adiola Allah, Aina Oluwatoyin Akinola Omotayo, Bashirat Oyiza, Daniel Irene, Daniel Orike, S.A. Juice, excellent. Genesis, people that appreciate Manuela, Mirana Salusi, Azaya Chinaza, Ofolabi, Peter Okechukwu, Philomena, Rotimi Owolabi, and Ubochoma Messi. You all are well appreciated. It is not easy. I will always keep appreciating people because it's not easy. One, in this country where we have not even eaten 3 square meal, we are paying money to learn. So I really want to appreciate that. It is. If it was easy, then more than 1,001 persons would have joined the class. If it was easy, but it is not easy. When you want to pay money for a training, there's this thought that will come to your mind. My friend, what do you even want to learn? Once you have learned, what have you done with it? So those thoughts came to us those days when we are preparing ourselves. Any training we see, we pay, we shoot head. We never knew that we are just preparing ourselves for the future. There was a year I traveled conference up and down. And let me just people attend conferences. So when you attend conference, you see people who are doing this thing you think they are doing better than you. The ones who think they're even better than you, exchange contact. So that year, we are traveling bomber to bomber just to make sure that we gather knowledge as much as possible. So once again, thank you for.
Hello, sir.
Yeah, I can hear you.
Sir, you made a mention of that your institute focus on research, from research to patenting, from patenting to maybe product.
Yeah, to products. Yeah.
Yeah. So like for us that have just started into this in silico research, we need to understand that any research that we are going to that you need to look at the previous studies. And you
Yes,
normally look for research, I mean, articles that are already published online. And one of your trainings that I attended, you made mention that like, is this in silico green chemistry? You may never
yes,
found any published articles online. So, so like in your own case, so how do we start to do all these things since we do not have any prior research to fall back on?
yes. On that note, that is a gap in literature now because there is no. In fact, let me put it this way: there is no research that does not have literature available online. Now, what most of us what we are after is exact literature that hits directly to what we need. But that is not what we are after in research. When we are talking about literatures in research, we don't even want to see exact literature. Because if we see exact literature, that means that work has been done. But we are looking at related literatures. So now take for instance that you are working on in silico bioremediation. And from literature, there is no work done on in silico bioremediation. You can now look out for related literatures on in vitro bioremediation. So people have done bioremediation in bench work in vitro. So those literatures now forms your literature review, your related literature. Then you now have to state the gap in literature that based on findings, there is no in silico green chemistry, there's no in silico studies on this bioremediation, and this has necessitated the need for the present study. So use the ones that are on lab work, on bench work to form your related literatures. That is the only thing we do in research here.
So that will form justification for the study.
Good, yes, good. So that is how it is. How which, as we are like this, God will provide for you to join green chemistry in February.
Yeah, by God will, I'm doing that
Yes,
class.
yes.
By God's grace. By God's grace.
So you know, sir, I have been your student.
Great chemistry. Oh.
No. Salusi is you are ever asking.
To join great chemistry.
No, Salusi, I'm owing you a prize, yeah. I have something in mind. I'm working on something for you.
Okay, sir. Thank you, sir.
Yes,
Thank you so much,
something
sir.
you're working out for.
And me too.
And to everybody, to every one of us.
All right. Thank
Thank
you, sir.
Yeah. Once again, thank you. Good
Thank
night.
you, sir. Good night. Thank you.
Good night, sir.
Thank you.
Thanks, sir.
Good night, sir.
So
Yeah, thank you.
I sent that stuff to your DM, the issue I'm having with my installation. I don't know if
Okay. Before I go back to duty tonight, I'll look at it.
all right. Thank you very much.
Thank you.